Okay, I guess we will start. So, good afternoon everyone, dobro poslijepodne, dobar dan i dobro večer između negdje za sve prisutne. Našli smo se ovdje na SUZI Zoomu da slušamo predavanje dr. Safaka Arslantürkoglua o ponašanju zidova od cigle za opterećenje koje je izvan njihove ravni i obično se manifestuje tako što zidovi od cigle počnu da ispadaju iz ravni iz zgrade i padaju na ulicu ili unutra u zgradu i time ne dovode tipično do kolapsa, ali do dosta oštećenja i opasni su po život ljudi. Tako da ovo predavanje će držati dr. Safak Arslantürkoglu koji je na ETH-u kod mene uradio doktorat pre otprilike 2 godine. Posle toga je napravio svoju konsultantsku firmu Leo Consulting i pre nego što je došao na doktorat na ETH je bio zaposlen kao inženjer u firmama u Nemačkoj i Švajcarskoj. Tako da imamo jednog gosta koji je pola akademika, pola inženjer iz prakse. So now I will switch to English so that Safak also knows what I said. Safak, I introduced you briefly and I said that you're going to talk about the out-of-plane behavior of masonry, unreinforced masonry walls, a topic that covers both your work in your PhD and also the work that you do in practice on evaluation of different buildings in Switzerland and elsewhere. So, Safak, please start the presentation, and then as you go, we will have to listen to it, and then we'll save the questions for the end.
Sure. Thank you very much, Professor, for the introduction. Let me start. So I will be speaking about the out-of-plane behavior of walls in unreinforced masonry buildings. Let me know if you cannot hear me, if I'm too fast, too slow, just let me know. So let's get going. Here is an overview about the topics I plan to cover. So the first, the most important part about the behavior and the mechanism behind. So why this is relevant for the assessment. I'll try to introduce the mechanism behind it and discuss why that is particularly relevant especially for masonry buildings. And then try to show you several examples of failure mechanisms also from the recent earthquakes. And then I will try to continue with the treatment of this type of behavior in structural codes and standards with a focus on Switzerland. So how we are dealing with these types of walls in Switzerland, also some relevance to Europe. It will be like 2-3 brief mentioning of the methods, and then actually the focus is on the rigid body kinematics. I will try to explain what that is, how to use it for the assessment of buildings, and to make in an attempt to make the presentation a bit more practice friendly. I will show you a case study example, and then we will go through the individual steps of calculation. So maybe you can, if you want, you can also try it on your own, and then wrap up the whole thing with a short summary and conclusions. So the mechanism behind, and in the literature on the out-of-plane behavior, one statement that is a statement in this statement in green probably is quoted more than almost any other sentence. And the Paula Christie, they described the out-of-plane response as one of the most complex and least or ill-understood areas in seismic analysis. To understand, let's look at 2 walls that are isolated, and these are subjected to different types of loading. We have the wall on the left that is experiencing an in-plane action. We have forces acting along its length. It can be, of course, shear as in seismic actions. It can be also vertical loads like gravity loads, self-weight, etc. So when we are dealing with in-plane loading of walls or structures in general, that that involves usually a check of the material. So we calculate the stresses, we check if the shear strength is enough, also compressing strength, stresses, etc., etc. So when we are dealing with a wall that is loaded perpendicular to its plane, that is an out-of-plane loading, there we have, this could also be the seismic excitation that may cause the wall to bend, or that may lead to a rocking outward, and this will eventually fall to fail, either partially or completely. So what we should differentiate here is the type of, or the mechanism of this behavior. In plane loading, we are usually dealing with materials, but out of plane is primarily a stability problem. So here we require to perform a stability check, and not always a material type of assessment, which is the main difference. So, and that sort of check, or that sort of this mechanism is particularly complex because there is the interaction between the behavior in plane and out of plane. So just to illustrate it, here is a building taken from Paula Priestley's book that is excited by an horizontal acceleration, a G that would excite this wall in red, this the facade wall. It will excite it in its plane, and then this input acceleration will be converted to or will become an output acceleration, and that output will be transferred to the floor system. So here we differentiate between floors that are flexible and floors that are rigid. And here, for instance, when we have a stiff floor like reinforced concrete, we can say it's usually able to provide or hold the walls together. So the walls are primarily loaded in their plane. So the difference is when we don't have that, it may be, for instance, a flexible floor diaphragm, as in timber floors. Then the response will be modified, and then the acceleration that we had at the ground floor, the ground acceleration, will be modified actually twice, from the red wall to the floor slab, and then from the floor slab to this green floor, which sort of shows or illustrates the complexity in that issue, or in this type of assessment. And here is a graphical example where what these look like. We here differentiate between this so-called box behavior, or we evaluate if this diaphragm can provide this type of behavior. If it does not develop a box action without a stiff diaphragm that would usually tie everything together, there is no real redistribution of forces between the wall planes. So if we have flexible floor system, walls tend to behave almost independently, as we see on the upper example, or a rigid diaphragm would provide, in that case, a global behavior. And here is an example in the sketch to illustrate this idea symbolically. If the walls or floors are well connected, we have the action, we have the effect of them being tied together like a package, like a strapped package. In this case, the building is able to provide or respond as a single unit. That means we can evaluate the response of the building usually on a global model, because we expect the building to deliver a global response. So again, that is not a case, not necessarily the case with the out-of-plane behavior. We cannot automatically assume that the building will deliver a global response. That means we require different types of mechanisms. We need to consider different types of mechanisms. And here is a collection by Diala and Speranza. We see how the possible out-of-plane mechanisms may look like here in each mechanism. A different portion of the wall is triggered, and that already shows the sort of the complexity we may face. Just to name a few examples, we have the mechanism A, the vertical overturning, that is a simple rocking of the facade, no contribution of the neighboring wall, so there is no connection with the orthogonal walls. That is typical when the connections are poor or when they're practically missing. we may also have different types like B1, B2, facade wall plus also the neighboring walls being involved in the mechanism shows just a different degree of connection between the walls. Or type C, corner failure, or type D, it can be also partial overturning, or if as in type F, if the wall has a ring beam on top or connected to the floor, to the roof system, we may then also expect this so-called vertical arching and so on. So a key point is that mechanisms A through at least F or also G, H, they have one thing in common. They have one common characteristic, and that is the activated wall segments behave essentially as rigid bodies. So whether only the facade is rocking or we have several walls that are moving together, the deformation is concentrated at the hinges, and while the wall blocks remain basically undeformed. So this is an important feature, and this is actually why simplified kinematic models are a suitable method for the analysis of these failure modes. So I will show you some examples how these failure mechanisms look like, again, based on some past evidence, past earthquakes. The challenge, as already mentioned, lies in the identification of the mechanism. So if you would have these buildings before the earthquake, it wouldn't be obvious which mechanisms were to expect in which types of fall. When we have the damage, then it's easy to assess them, but the challenge is here not the implementation of the method, but it's to tell which is the mechanism I would expect in this type of behavior. So when we have these sort of buildings with usually with soft floor diaphragms, for instance, timber floors, the task for the engineer is usually to check potential mechanisms that are that are likely to trigger, and then do a comparison. So the goal is to check which is the acceleration level that would trigger a failure in this mechanism, and usually the mechanism associated with the lowest acceleration is defined as the governing mechanism, and we should start usually from improving that system as a retrofit measures. I also have some more recent examples here from 2023 Turkey earthquakes. Shortly after the event, a joint team of SUZI and ETH organized a visit to the affected region with international researchers. With international researchers, and here are some pictures. So what we observed was a repeating pattern. Was buildings with flexible floor diaphragms here, typically those with timber beams. They are particularly vulnerable to out of plane because without the reliable floor to wall connections, the self-weight of the wall panel is usually not enough to resist overturning. As in this example, you see the wall has failed. And here another actually same building, but just on the front here you see in red a triangular hinge or failure, out of plane failure has formed underneath the roof, combined with some in plane cracks or in plane type of behavior. And here the same facade from the side. You can see here the wall, the rotation in this wall, and also in that example, we see this is a sort of this rigid body motion, rigid body kinematics example, because we see the wall rotates as a whole around its base. More examples, some from Hatay region near the old town of Hatay, where there were many buildings out of unreinforced masonry. And here, in a small number of cases, we observed ring beam-like elements and intended to stiffen the structure. These were not reinforced concrete beams. They were simply made from the same masonry units as the walls, and their presence is actually easy to spot. You see horizontal cracks and a clear separation along their length. So, but in general, there were no, or it was not very common to see connections between the facade walls and the orthogonal walls, as the one here. There's no connection, and here is the wall that has failed. More examples from Arsus, south of Antakya, a number of buildings where large masonry units disintegrated and fell out of plane. That usually indicates a lack of integrity within the wall itself. This is, for instance, common in structures or in walls with weak mortar or poor bond between the units. And here another building, like a textbook example. Here you see a combined failure pattern, first or just one after another. We see here in blue the X shear cracks with the X shape, opening cracks from left to right, and then closing of this crack, and then opening of another diagonal from right to left, and leading to this type of shear failure. And plus here you can see it from the sides. It's easier to spot that this red spot or this red area failing out of plane with this with the separation of the wall on top of the ground floor. More examples. Antakya. This is the Google Maps picture of a hotel building before the earthquake. Here, what we observe is what we see here is the complete facade of this hotel building, and this is the situation after the earthquake. We see here a complete or total loss of the facade of this hotel building. And we can see a clear separation and the forming of the hinge or the separation line above the just over the height of this building. Also, interestingly, we see here probably a recent renovation here for the floor system, but it was not enough to hold back the wall, and it didn't stop this facade wall from the out of plane failure. So to continue, I just want to focus on the treatment in codes and regulations. So what are out of plane is not covered in every code worldwide or international level. So there are some codes that do cover it, mainly Italian codes and regulations. They are leading in that, but when it comes to the assessment of out-of-plane behavior. Here I took an excerpt from from these sheets illustrating the need for the collapse mechanism in unreinforced masonry buildings, and this is a translation of the Italian text, and I will just read it. When the building does not show a clear overall behavior, but rather tends to respond to the earthquake as a set of subsystems referred to as local mechanisms, the check on a global model does not correspond to its actual behavior. In such cases, the global verification can be carried out through an exhaustive set of local verifications. So this is a very important statement or very important information that basically says no matter how complex the global model, no matter how precise the modeling approach, if the building does not show a clear global behavior, and if the software focuses on the global behavior, which is a very, very, very common thing, then the outcome of the model is not going to be representative of the actual outcome, because again, we automatically assume that the building will show a global behavior, but this is not necessarily the case always, especially with buildings with flexible floor. So that approach or that information that acknowledges also the fact that if the structure cannot act globally, then we should also not model it globally, a very important thing. So I said the focus is going to be on the Swiss regulations, and that is why I think I need to shortly introduce the concept of the Swiss code, that is the SIO 269-8. This is the code for the seismic assessment of existing buildings. So in the SIA code, we have this so-called risk curve. That risk curve just illustrates the compliance factor on the horizontal axis. The compliance factor is defined as the capacity to demand ratio. So it basically tells or compares the structure of the or the capacity of the structure. So the structure can provide a capacity. So that is divided by the code demand for an hypothetical identical structure, gives the compliance factor. So it's basically capacity demand ratio. On the vertical axis, there is the so-called unit casualty risk. So that sort of corresponds, or that is a measure for the likelihood of getting killed due to an earthquake. So if a person is to occupy a building, that corresponds to the likelihood of this person for getting killed due to an earthquake. So that is the risk curve. So this is used. So the Swiss code uses this curve to make to support engineers for the decision making, and they differentiate actually, or they define 3 zones. So the green zones is prescribed for new buildings. So here the compliance factor is 1.0 at least or higher. That means when we design a building following the code, then we can then actually we make sure that the compliance factor is 100%. Then there is the second, or there's the lower threshold, that is the red region, characterized by an alpha min. This alpha min is for regular residential buildings with normal occupancy. It is declared as 25%. So buildings, they have to provide 25% code compliance at least. If a building has a lower code compliance, then it is said to be in this red zone. In this red zone, we require measures to retrofit this building. So no matter how high the costs, the code tells you have to implement them. Existing buildings are usually in this yellow or orange region between alpha min to 100% compliance. That in that region, we have to perform an assessment called the commensurability. So that is actually a term for the cost-benefit analysis of a retrofit measure. So what we do here is we just look how many years the building is expected to serve, what is the service life, how many people are living in there, and how much is the cost of the retrofit. And then there's the assessment of cost-benefit. So if the risk can be reduced with a reasonable financial cost, then the retrofit is to plan, or is to be done. If not, then the existing risk can be accepted. So this concept is important because I will use it, especially this alpha min corresponding to 25%. So in the Swiss codes, for the assessment, the first mentioning of out of plane was the so-called Backblatt 2018. It's a leaflet that is now superseded by the code that is active today. So in this Backblatt 2018, there was this table providing a simplified slenderness criteria. So Switzerland is divided into different seismic zones, and depending on the zone, this table required for certain height to thickness ratio, so basically slenderness ratio, if a wall can satisfy this criterion, and then the code assured that the compliance factor is at least alpha min. So for regular normal buildings is 25%. And similar thing is also in the implemented in today's SIA 269-8. It just looks a bit more complex. It has a couple of more parameters. These parameters usually has to do with the boundary conditions of the wall. Here, I try to give an example, depending on the on whether the wall is a cantilever wall, whether the ends are pinned or fixed, or one side pinned, one side fixed, etc. With this equation for this example building I used here, you can obtain the minimum required wall thickness. Again, this equation only serves that, with this equation, you can only show that the compliance factor corresponds to alpha min, basically 25%. So in both cases, the older code is not anymore, cannot be used anymore, but the concept was more or less the same. You can show that the compliance is alpha min. If you require higher compliance factors, then these are not helping much anymore, so you needed something else. And this something else was in the older code, in the leaflet 2018. It was the Pauli-Priestley method. I'm not going to mention that in detail, but just to mention it shortly, the code was recommending, the older code was recommending this Pauli-Priestley method if higher compliance needs to be shown. And this is a check mainly based on the material parameters of masonry. Especially, it depends very much on the stiffness of the material, which is not easy to assess if you're dealing with existing buildings. So I'm not going to be mentioning that in further detail. The method is mentioned in this Pauli-Priestley book, and it was also a part of this SIA technical documentation, which is why in Switzerland it was, or it is probably still, it's been used heavily when it's about out-of-plane assessment. Many engineers use the Pauli-Priestley method. And then there is the other option, other assessment method, that is the rigid body kinematics, or also known as the Griffith method. In Switzerland, this will probably be the standard method, if not now, probably in the near future, because there's this documentation published some year ago implementing this methodology. I will talk a bit more about what is exactly meant with this rigid body motion, how this behaves, what are the assumptions, but that is going to be probably the standard method in the near future in Switzerland. But in Italy, it's been in the code for quite some time. Also in the older versions in the Italian NTC and also Circolare, they were using this methodology, and this FOAM documentation in Switzerland has a very close resemblance to these Italian approaches. So what that is, rigid body kinematics, and here I will try to illustrate a wall that is in this gray color. That means the wall is loaded only under its self-weight plus vertical load, so no earthquakes yet. Then wall turning red means the wall will start to rotate. This rotation is caused because there are some horizontal accelerations representing the earthquake. And then we have this alpha 0 that is called that is the acceleration that would trigger rotation in this wall. So we need the wall to reach this measure, this value, so we can see rotations in the wall. So if that happens, and then the wall will start to rotate with increasing displacements d until the acceleration is 0, and there we have the maximum displacement. And here, what you see here is blue is actually just the basic version of, this is actually nothing different than a capacity curve for this wall. You can see it like a pushover curve, just in a very simplified version, and just for this wall, for this simplified check. So this is how the method actually, or this is how the failure is modeled in rigid body kinematics methods. There are, of course, some underlying assumptions we have to check when we want to use this method for the assessment of existing walls. And the assumptions are that the wall consists of rigid macro blocks. So we may have wall on top of, or different walls on top of each other over the height of the building. So what we assume is, we say that each wall or each portion of the wall is a rigid macro block. That is the first assumption. What we also assume, that we say that a sliding cannot take place in the wall, so the sliding is prevented. That means the failure is actually a type of rotational, or is a result of rotational movement. So no sliding is involved. And the last criterion or last assumption is that the monolithic nature of the wall is preserved. That means even when we observe failure, a certain nature, certain monolithic nature of the wall is going to remain. And with that, we can, or when we assume this history, or when we do this assumptions, then we can use rigid body kinematics. You can also see an example here, some figures on the right-hand side, with on top the examples of simple rocking around its base O, and then we have this rotation theta, and in that case we only have one theta because we just have the rotation around the base. Whereas when we have a wall that is simply supported, then we may have a hinge at the mid height. In that case, we will only have one rotational angle, but we don't necessarily have to have this hinge at the mid height. In that case, we may have theta 1 and theta 2, and they don't have to be equal. So it can be reach different values. So in an analogy to global behavior, also here we differentiate between force-based and displacement-based methods. So force-based are usually termed as the linear kinematic methods. So and displacement-based ones are the non-linear kinematic analysis methods. So what we do here in the force-based approach, we solely focus on the onset of the mechanism. So what we do here, we just look for the acceleration that would cause the wall to rotate. And displacement-based starts where force-based analysis ends. Here we are dealing with displacement. One important consideration here is we should also check if the rotation happens at the base of the mechanism or at a certain height in the building. So when it's at the zero level, then the capacity demand ratio is defined as the acceleration capacity. So the acceleration level that would cause the building to wall to rotate over the ground acceleration, because the mechanism is on the ground level. If not, then we also have to do consider the amplification of the acceleration within forces or amplification of the displacements when we are dealing with the nonlinear analysis. So yeah, let me show you an example how to assess this method. It is going to be an existing building from Switzerland. For those who are interested, this building is also mentioned in the in this SIA documentation 237. You can find exactly the same building. It is a 4-story administrative building constructed in 1912. A facade of the building, and here you see in this red circle the central part of the building, and the focus is and also to mention on the table on the right side we have the seismic zone. So we have zone 1A, that is the seismic zone with the lowest hazard in Switzerland, with a PGA of 0.6 meter per square seconds. And then we have the corner, so the spectral shape parameters. The soil factor is set to 1 because we have soil class A, and then the importance factor is also, just for the sake of simplicity for this example, set to 1. So when we are dealing with this building, the material criteria are not as important as in plane analysis, because again, when we are dealing with the rigid body kinematics method, we are approaching the problem from a stability point of view. So what we require here is, of course, the self-weight of the masonry unit. So here we have square stone block masonry with a bit heavier than or almost as heavy as concrete. The compressive strength, it is not completely out of consideration, but again, it does not have a dominant role. And then, as in global assessment, we have some factors for safety factors, or we have factors for the capacity and for the demand side. So capacity reduction, I set that to 1, again, sake of simplicity, and demand reduction in comparison to behavior factors in global analysis, I set that to 2.0. So you see here the floor plan of the building on the left. We are focusing on the central part of this building, and here what we have to, or we are going to focus on the facade walls. So what we are going to do is to take one facade wall, one of these short walls, because these are repeating. So we can just take one wall, one short wall, and make a statement about the rest of the similar wall, just from analogy. And that's what we are going to do. Another important thing is out of plane is also heavily connected to the type of floor system, whether we have the diaphragm action, box behavior, yes or no. That's exactly what we do here. We have to check the floor system. We have here timber joists. This has a timber beams, the floor system, and it's very common that these walls in X direction, these short walls in X direction, usually they act as support for the timber floor. So most likely we have beams from this from the facade until the middle of the mid-axis, and then from the mid-axis to the other end. And for what we have to do is we have to define the loads, because they will lead to these rotations, or they will stabilize the wall. We have to just consider these actions, and for that we need the story loads. So here I just have the self-weight plus some additional load plus 30% of the live loads. For a classical story, it is 2.6 kilonewton per area, and in the attic floor, they're just a bit higher. So what we need here, or what you see in red, is the tributary area for this wall 14 that is selected for the analysis. Here we have to differentiate between the area for the vertical load and for the horizontal loads. What you see here is for the horizontal load, so it goes up until the mid-axis, just because we assume the timber beams are here from the one facade to the mid-axis and from the mid-axis to the other facade. So that's why the consideration. So just to just to go through our assumptions again. So we have to make sure that these three assumptions are still holding, or that these are still valid. Plus, we will check if it is recommended in the Swiss regulations that the utilization of the axial load does not exceed 30%. That is because if the axial load is too high, it may then lead to deformations due to this axial load. So that's why it is recommended in the Swiss code that this check is done and utilization is smaller than 30%. This criterion is actually not very hard to satisfy in the assessment. And then what we are going to do is we will say, okay, we have this wall over the height of the building. So this is the facade wall. And then we have a hinge at the base, and it forms at the outer edge of the wall in the direction of the failure mechanism. We also say that eccentricities are not there. I mean, we can also have eccentricities, but again, for the sake of simplicity, that's why here the remark that the assumptions in italic, they were made just for the purpose of this presentation. So we can have other assumptions, but in that case, we have to adjust the loads or also the structural model. So here we just continue with the loads, and what we have to do is we have to have these blue loads, the forces. These are the self-weight of the wall. We already have them per story, and then we have the story loads. So the wall load, self-load of the self-weight of the wall, the blue ones, these are concentrated at the mid-height of each wall. Plus the story loads, these are these are at the top of each floor or each wall, because the loads are transferred from the timber to the wall. And here are the forces. I also did this check with the Tremoli software just to see, and there's a quite good match. And then we can continue and then focus on the horizontal loads. This is the essence of the rigid body motion, rigid body kinematics. So what we do here is we already assess the self-weights. We know how big they are. So we solve they are roughly 200 kilonewton. What we don't know is we don't know how large the horizontal loads are. So what we can do is, or what we know from equivalent lateral force method as in global analysis, there we just say, based on the spectral acceleration, some portion of the mass I have to consider as an earthquake excitation. We do the same thing here. Instead of saying some portion of these 200 kilonewtons, we just say alpha 0. So that is basically the portion of the vertical load that acts as horizontal loads. Since we don't know how large this portion is, we just, instead of giving a number, we just call it alpha 0, and exactly that is the triggering acceleration. So what we do is actually we are searching for this alpha 0 that would trigger a rotation in this wall. We just continue with the horizontal story loads, same logic, same principle. As a ratio of the vertical loads, we define them. They are different in classic story and the attic, of course, we defined already. And then here is an overview of all the applied forces. So what we have to do here is, one thing is we need the axial force at the wall base, just the sum of all the forces acting. We have the compression zone, so that is just just an illustration of this of the compression zone. That is basically the rotation point for this wall. And then with that, we can say, okay, now we have some forces that are acting. Some are vertical forces, some are horizontal forces. What we have to do is to observe what is going to happen with this wall. So the wall will rotate with this phi rotation. Of course, it's an exaggerated manner, just for clear visualization. Again, the vertical loads from self-weight and story loads plus the horizontal loads. Now I have everything. So what we have to do is here, we have to use the virtual work principle, or it can be also the moment equilibrium. It will lead to the same thing. So what we have to do is, what I'm going to do is, we just need the virtual work principle. So we need each force times these virtual displacements that will give the work. So that's what I'm going to do here. We have to define the virtual displacements. These are the ones in yellow, just from basic trigonometry. Same thing for the vertical displacement. Then I can finally say, okay, each force is causing or delivering a virtual work. What I have to do is I have to differentiate between the forces that are in favor of the wall. These are the stabilizing ones, and the forces that are causing the wall to rotate. So what I'm going to do here, just differentiate between these two and say, okay, forces that act horizontally, these cause the wall to rotate. So these are destabilizing. Forces that are vertical, they actually help the wall not to fail, and these are stabilizing. And we have to make sure that these are in balance. And when we solve the whole thing after alpha 0, and then it will give us this 0.035. And that is exactly what I'm looking for, because that is called the horizontal load multiplier. It basically gives the ratio of horizontal to vertical forces. In other words, it means a rotation in the wall will be activated if 3.5% of vertical load is reached. You can see this is a rather low number, especially in comparison to the equivalent lateral force analysis when we are dealing with global behavior. And then the capacity is defined. We just add this G, so the units are matching, and gives us the capacity about 0.4. And then the demand is derived from the peak ground acceleration, plus we have this behavior factor, and their ratio gives the capacity demand ratio, or the compliance factor, as we call it in the Swiss code. And then, of course, one is also interested, okay, how that software would get this number. And to answer that, here is an example to the software Tremuri, just same facade. Basically, the mechanism that is active or assessed is the one in pink. And here you can model it in Tremuri, and then it will show you how this would behave. Exactly the same thing, same what we did in the hand calculation. and this is the outcome. You see the capacity over the and the demand in comparison. Here, for a better overview, with the hand calculation, we were a bit slightly on the safer side. This can be also a rounding error, by the way. So we have a very good matching between the capacities, demands also for the load multiplier and also the compliance factor. And the reason for that is because what we do here is we are looking at isolated walls. So of course, global behavior is not that easy to assess by hand, but here for the hand calculation, actually it's a very convenient method, rigid body kinematics, because we are dealing with the walls that are isolated, and we can do this comparison. So the question to ask is what the challenge actually is, when we are dealing with hand calculations. So the challenge is not the nature of the problem, it's not the nature of the definition. The rigid body kinematics is really very intuitive, it's easy to implement, but there's still a challenge, and that challenge is that we basically don't know which mechanism to explore. So imagine we can have this wall with simply supported at both ends. The challenge lies in the identification of the mechanism, because we don't know where the wall will form a hinge, or which support conditions will effectively remain active, or the position of the lower and upper restraints, they may behave differently across floors, or plastic hinge does not have to be always at the mid height, even though it is common to assume that in this type of assessment behavior. It can be also further mechanisms. This would look like that, for instance, but it can also be further mechanisms. We have different heights for the supports. Hinge not necessarily at the mid height. It can be at the floor level, because there may be additional horizontal loads that may trigger a sort of rotation in this wall, or it can be different heights, not necessarily at the floor intersections. It's also common to expect sort of this mechanism in upper floors, because here the axial loads that are actually in favor of the stability, because they stabilize the wall. Here the axial loads are rather low, and then the demands are rather high, because the ground acceleration is amplified over the height of the building. So here it is also worth to take a look and do this consideration. And you see here the challenge is actually not in the implementation, but it's just the number of required assessments, and this can be a tricky thing. So to sum up my points, let me conclude. For masonry buildings with flexible floor diaphragms, local mechanisms often govern the seismic safety, and if we implicitly assume that the building would behave as an integrated box, then we risk an overestimation of the capacity, because many existing buildings, especially those with flexible floors, they don't provide this diaphragm behavior, or they don't have this wall-to-wall connections that are required for global behavior. And with a focus on Swiss methods or Switzerland, in Switzerland, two methods are commonly used for the assessment of out-of-plane behavior. The first one is the Paula-Priestley method. This was also implemented into this SIA documentation, and probably one of the reasons why it's a popular method in Switzerland. And then we have this more recent document, that is the FOAN, that is dealing with the rigid body kinematics. It's a different approach, it's an alternative approach. And then the advantage is it does not rely heavily on material parameters, where the uncertainty is large, but it considers the problem or the assessment rather from a stability point of view. So the rigid body kinematic, rigid body motion is a valuable alternative to Paula-Priestley. Of course, assuming that the assumptions, or provided that the underlying assumptions are satisfied. And across all methods, the main challenge is always in the definition of the kinematic chain. So regardless of the methods, the challenge is indeed the definition of the governing mechanism, because it is not obvious to tell which mechanism is likely to occur. and that of course dictates the outcome of the assessment. So this brings me to the end. The examples, the ones from Turkey, they are based on field observations, include the ones from 2023 earthquakes. Here is a picture of from our visit to Turkey, organized jointly by SUZI and ETH Zurich. So I would like to acknowledge my colleagues who took part, and also I want to thank SUZI for the invitation, and of course to all of you for your time and interest, and I'm happy to take any questions. Thank you.
Okay, thank you, Safak, for this presentation. As you see, there's quite a bit of the experience from the field was obtained in this shared mission. And as you all know, SUZI also took part in 2 other missions, actually 3, 2 in Croatia and 1 in Albania, which also had similar out-of-plane failure problems with masonry buildings. And the report that we published about the Albanian earthquake has also observations of this type. Are there any questions from the audience about Safak's presentation? Da li imate neka pitanja? Well, if there doesn't seem to be any, but let me well, first of all, let me ask if the documents, the FON document and the SIA D027237 are available on the web somehow. The FON documents should be for free.
Yes.
And I think both are.
The 237, unfortunately not.
Okay.
Yes, it needs to be purchased from SIA as far as I know. I can check, but I'm quite sure that it's not available. But the FOIA documentation, it is available, yeah. And there are also some complementary, some SIA documentations that are accessible. So let me know if someone's interested. I can also send them the ones that are accessible for everyone. But FOIA, it is accessible. Yeah, it's accessible for everyone. Yeah, and it is the main thing now because it deals with the rigid body kinematics method that is likely to become the standard in Switzerland. Also, I think in Eurocode in the draft, it is the method that will likely be implemented.
Yeah, that is so. And then in terms of this rigid body kinematics method, there are many mechanisms.
Mm-hmm.
So how do you suggest that people, I mean, how do you in practice deal with exploring all those mechanisms, basically 1, 2, 3, 4, 5, 6, 7?
Yeah.
And how is there, I mean, what would be the way to go? Spreadsheets, by hand?
Yeah.
Some kind of a more sophisticated code. What do you recommend?
Yeah. I mean, one uncertainty is, just 1 second. So one thing is actually to define here. I don't know if you can see my mouse. Probably you cannot, right? You don't see.
There's something was flashing. Yes.
You see. Okay. So one thing is, it doesn't have to be, like this rectangular wall. It can be also some portion of the wall. So this is really tricky. But what can be done for practice, or what I try to do is, so once I define this 2D, for instance, this 2D mechanism, when I have this simply supported system. So what I do is one can assign and say, okay, I'm not certain about the position of this support, of the lower support, of the upper support, and of the hinge. What I can do is it's actually, one can assign like random numbers. So say, okay, the position here, bottom is 0, top is 1, and hinge is between 0 and 1. So it's actually an optimization problem. So one can say, okay, so if I have an Excel spreadsheet for that, which can be done easily, then I can say, okay, so just create 100 scenarios with varying heights for the supports plus for the hinge, and then for each case one can obtain the horizontal load multiplier, and usually the one with the lowest value is said to be the governance mechanism, and that can be. So this can be automated. This is actually possible, yeah. But the challenge of saying, which portions of the wall, it is tricky. So as far as I'm concerned, there are some attempts in publications for the automation, but it's not an easy task. So yeah, some things can be automated, but yeah, it's still a bit tricky.
Yeah. But I mean, based on earthquake experience, it's very, very, very common to have the top part of the building, the parapet of the building fall out because of the very small axial loads.
Yeah.
And that one of the last mechanisms you have in this figure, if you run the whole animation, that one.
Yes.
That one is something to check for sure, and perhaps the global one or two of the global ones, but certainly it can be automated, and I do not know if there is any software that does it. But do you think that Tremuri inside itself has anything like this, or is there any software, commercial software that has something like this inside it already?
I know there was an attempt in research based, I mean, it goes into with the geometric modeling, but in Tremuri, the user actually when I have this facade, as a user, I have to tell Tremuri, I have to draw this pink shape to tell Tremuri this is the mechanism I expect. It can be also a corner type of failure. So that is not automated, unfortunately. I don't know also any commercial software that does it. So it is, I mean, I have to do the user have to do this definition. But once the mechanisms are there, the calculation is quite fast. But again, it has to be done one by one. And there's, actually, it's infinite number of possible mechanisms. So it's also a bit based on experience to expect. Maybe here I expect a corner failure, or here maybe a rooftop, or in the attic because of, as you said, low axial loads. So there's some automation, but the definition of mechanisms, this has to be done by the user. Yeah, that is the challenge.
Yeah. I mean, I agree. And for some of the younger and more computer proficient attendees, that's an opportunity to perhaps develop something that could be useful for a lot of people doing this in practice.
Yes, exactly.
And one other question, one thing that I know we struggled in research and also in practice is determining the properties of these walls, strength or even thickness, based on existing drawings and possible changes that the owners have made over time, like that building in Turkey that was supposedly retrofitted, but not much was helpful. So how do you go about preparing the input data that you have confidence in?
Yeah, I mean, luckily in the rigid body motions, I mean, the main part where materials are important is actually just for the depth of the compression zone, and that for sure has an effect. But I mean, it is limited. So, but the main thing is actually for the assessment I would do, or I mean, I also do consider is whether there's a connection. Just to at least to limit the number of mechanisms I have to assess. So is this the cantilever wall, or is it a simply supported, on both ends? This, for instance, I can rule out cantilever if I do the assessment on site, and if I see the wall is connected to the roof or to the orthogonal walls in the attic floor, then I can rule out cantilever, and I can say, okay, that reduces the number. So this is actually already a great help. Or when I have to do some more in-depth investigations, like destructive testing, I can do some, I can do a very conservative analysis, and when I can say, even with the cantilever assumption, the compliance is actually over 100%, then this also reduces the number of required, pick hammer investigations or destructive testing. So that can be used, mainly for the, I would say, for the reduction of the, cost. It's basically also a financial consideration when I can assess some mechanisms in advance, just to rule out some mechanisms, and that helps. But luckily the materials are not that relevant for that type. Yes.
Yeah. So in that sense, going out to the building would be a good thing to do. It could save a lot of calculations, save a lot of money to the client. And certainly just looking at the situation helps a lot without actually knocking out some bricks or doing some material tests.
Definitely. Yes, okay. Definitely.
Yeah. Good. Well, thank you. Well, anybody else? Perhaps there was another question or two that came up in the meantime. Ima li još nekih pitanja? Da li ste se nečega setili u međuvremenu? Well, then if not, then the thing to do is to thank Safak, then Dr. Arslantürkoglu again for this presentation. It will be recorded, and at some point soon it will be posted on the SUZI-SAEE's website, and this we do with the access through the user password, so that the members can access it for sure. And hopefully there will be a couple of more people or a bunch more people watching the video when they can. And if there are any questions about that, please try to relay them through myself or Dr. Vladimir Vukobratovic, who would then take it over to Safak and hopefully provide an answer to you as quickly as possible.
Anytime.
Yeah. So with that, thank you, Safak, and
thank you very much,
to the audience, and see you at the next seminar. Bye-bye.
Yes. Thank you. Bye, everyone.